So yeah, I'll be also talking about unbalanced PSI in the unbalanced setting. And this is work with my colleagues at the University of Waterloo, which we were able to call PEPSI. So the outline, just high level, will be, first I'll just go over some of the definitions, unbalanced PSI, and some of the other work that's in this area and why they're lacking. Then I'll go over our construction, how it works, and then the approach we had to optimizing PEPSI and parameterizing it. And then I'll go through our evaluation in several different settings. All right, so first, the setting of unbalanced circuit PSI. So set intersection itself, we've seen it come up a lot in many applications as a important step to do various things. For example, in contact discovery, you're intersecting a user's contacts with the user base of a service. In password checking, you're intersecting your passwords with a set of compromised passwords. And the common thing in all of these cases is that you just want to conceal everything outside of the intersection and reveal nothing but the intersection. And then circuit PSI is, as was mentioned in the previous talk as well, just taking that a step further and saying, okay, I want a function of the intersection, not necessarily the intersection itself. And the work of Kacsmar et al. A few years ago, for example, proposed doing differentially private operations on top of the set intersection. But there's, of course, many functions you can imagine that you would want to compute over the intersection. So on top of that, the kind of setting that we're interested in, because it's unbalanced and due to the examples we encountered, is imagining a kind of a client-server setting where you could have one entity which is, like, in some sense, more resource constrained, also has a smaller set that wants to find the intersection with a larger set held by a server, which usually has more compute power. And so you want to kind of take advantage of this imbalance in some sense, because the client may go offline. You can't rely on it to participate in the protocol as actively as the server. So the question is can we have a good circuit PSI protocol for this setting where we have an unbalanced set and we have a client that may not be able to participate in the protocol as actively as the server? So the reason many of the existing works in the literature may be lacking for this is usually one of three reasons. First is they're just too interactive to assume a client that could be like a mobile phone or like a personal device would be able to participate in the protocol and exchange a bunch of messages. You can't expect them to be online all the time. The other shortcoming and this is usually the problem with many of the MPC-based approaches that have any sort of two-party computation or multi-party computation in them. The other drawback of some approaches is that they have communication that depends on the larger set, so that's also not taking advantage of the fact that you have one of the sets is much smaller. And lastly, even if the other problems are addressed, some works just cannot extend to doing any other functions, or they just have the ability to compute only a limited set of functions, and going beyond that will require just redesigning the protocol entirely to compute a different function. So addressing those things simultaneously, we propose our protocol, PEPSI, which is going to be non-interactive. The communication will only depend on, will only linearly depend on the smaller set, and we'll be able to compute functions on top of it easily at very small cost after we've computed the original intersection, and especially with less cost to actually develop it. So with that, we can go. I'll explain our construction, PEPSI, and how it works. So the kind of first, or the building block of this approach is just using equality operators, where we'll be actually comparing elements from the client with elements from the server. And the main tool we will be using for that is homomorphic encryption, where we'll be encoding the client elements in a specific format to be able to compare them on the server side. Now, if you just take a naive approach to this and encode elements in a binary representation and then use a kind of folklore equality operator on the server, this would not be a good approach, because the multiplicative depth of that circuit would be high, and then it would be difficult to evaluate it using homomorphic encryption. And this is what the work of Kacsmar et al. Kind of showed, which we'll see in the evaluation, that ended up being very slow. So instead we resort to more a better equality operator for homomorphic encryption, which is the constant weight equality operator that we worked on 2 years ago, represented here at USENIX. So the gist of it, without going into too much of the details, is that we'll be representing the numbers in a specific format as constant weight binary strings. And by constant weight, I mean that the number of ones in each code word is fixed to a parameter h. And by representing all the elements in this specific format, you can then have a very low depth equality operator where the depth of the circuit only depends on the Hamming weight, the parameter h that you can choose, instead of the bit length of the numbers, which is the case for like a folklore equality operator. And this way, you can reduce the size of your, reduce the parameters of the homomorphic encryption scheme that you're using, which in turn results in faster operations and smaller ciphertexts, etc. The other kind of benefit that you get also by resorting to homomorphic encryption and using this specific equality operator is that you can then, you have a very SIMD-friendly operation that you're doing, so you can compare many client elements with many server elements at the same time by using an equality operator like this. So this is kind of like the core building block that we have there to compare numbers with some modifications, but we still have to resort to many of the existing techniques in the literature and some additional optimizations. Binning, for example, is very common. It was mentioned in the previous talk too. Nice thing about PEPSI is that it's compatible with any of the binning techniques that exist in the literature: cuckoo hashing, dual hashing, normal hashing. And on top of that, and that helps us reduce the overall number of pairwise comparisons that we have to do between client and server elements. On top of that, we use permutation-based hashing, which, while asymptotically it might not seem it makes a big difference, but because of the use of homomorphic encryption and everything is a homomorphic ciphertext, this has a very concrete effect on the number of, the difficulty of the equalities that we have to do. So it makes things a lot faster. And overall, by doing all these tricks, particularly because of their use of the constant weight equality operator, we can resort to tighter FHE parameters, which makes everything, both the ciphertext smaller and all the subsequent operations faster as well. So putting these together gives us PEPSI, but and the flow of the protocol, once you have all these steps, is very easy. You just need the client to encode its set, the client which holds the smaller set, encodes its set in that specific format in the bins with that specific constant weight encoding, sends it to the server does the processing, and simply has to send the result back to the client. So a very simple flow for the protocol. But the problem is we still have to parameterize all this because now we've introduced some extra complexity. There's of course the parameters that existed before, like the cryptographic parameters, the binning parameters, but on top of that now we have the Hamming weight, which is a property of this equality operator. So I'm going to just specifically explain how to manage that specific parameter. And the metrics we would want to optimize as we're choosing the parameter is the communication cost, which is easier to analyze because you can analytically compute it, but we also want to minimize the computation as much as we can, which is a bit harder, and we do that through micro-benchmarking specific steps to isolate the effect of the Hamming weight on the runtime. So on the graphs, like on the top graph, you can see the effect of the Hamming weight on the communication cost, which it's maybe a little hard to notice, but there's a range that has the minimum communication. And then on the lower graph, you can see the same effect for the computation, which there's like a range that gives you a better runtime and a smaller runtime compared to other parameters. So combining these two, there's of course some edge cases which are not good for either communication or computation, but there are, in the middle, there are some options on the Pareto frontier that you can choose from to decide whether you want like better communication or better computation or like something in between. So with that, now I can go to the evaluation. There's many settings that you could compare this work with, like settings that are interactive with ours that is not interactive. But I'm going to just, at least for now, just focus on just two specific settings. First is the actual non-interactive circuit PSI that's similar to ours. And then circuit PSI that might not be interactive, and I'll also compare with that as well. So in the case of non-interactive circuit PSI that is the same as ours, there's only DIPSI by Kacsmar et al. That we could compare with, because that's the only other work in this model. Now, their work, because like I said, it's in the same model and it's only sending the client set over the network, it can be asymptotically optimal. And ours is somewhat similar in asymptotics, but it's hard to precisely compare because now we have the new parameter, the Hamming weight. But the thing that you can definitely notice is the multiplicative depth, where, as I kind of alluded to before, is in the case of DIPSI, the multiplicative depth depends on the bit length of the elements you're comparing. So it could go up very quickly if you're comparing like larger numbers. Whereas in PEPSI, it only depends on this Hamming weight that we've chosen, so you can kind of control that parameter to make sure it doesn't grow too big. And then this translates directly to the concrete evaluation results, because you can have smaller parameters. And this shows in the experimental results as well. For example, just taking the first row, which is 1 million server elements and 1,000 client elements, and I think these are 32-bit numbers, if I remember correctly, that we're comparing, or maybe 16, I don't remember. But you can see that DIPSI has a runtime of hundreds of minutes with hundreds of megabytes of communication, but resorting to our protocol with like the better equality operator and whatnot, you can get to a runtime of less than a second with only about less than 5 megabytes of communication, which is about 4 orders of magnitude improvement over DIPSI. So that's one setting. That's one kind of one of the related work that we compare to. And then another one is the circuit PSI solutions that aren't necessarily non-interactive like ours. So there's like an aspect of latency that you would have to consider, but we'll set that aside for now. We just want to compare runtime and communication. So in this table, there's the work of Ion et al., which I think was mentioned in the previous talk too, that does PSI sum, meaning the function that they compute over the intersection is a sum of some attributes associated with the intersection. And the first kind of difference between that work and our work is that, well, ours can do this specific function, but you can also implement homomorphically any other functions that you would want. That's one advantage. But in terms of runtime and communication, you can see that we still get better runtime and better communication, despite the fact that we have a more generalizable protocol. And this is due to the fact that, at least the communication specifically, is due to the fact that they are sending something proportional to the larger set over the network. So they are not very good in this unbalanced setting where one of the sets is much smaller. So yeah, with that, I went over a protocol DIPSI and how it works and some evaluation. I'd be happy to take any questions.